So next will be Bobby Jackson. He's going to talk about arming the edge using machine learning at the edge to improve cloud microphysical observations. Go ahead, Bobby.
Okay, I'm going to share screen. Okay. So today we're going to be talking a bit about arming the edge, which is going to be using edge computing to improve Doppler LiDAR observations. This project I'm working on with Scott, Nicola, Pete Beckman, and Raj, all of the scientists that are involved with the SAGE project here at Argonne, and it's funded by Argonne's LDRD program. So, but I also acknowledge the LDRD program as well as the Argonne Climate Research Facility for providing the instrumentation and funding for this research. The next slide. So as Scott went into earlier, this is part of an NSF project. This is what I will introduce today is a sister project to an NSF project called SAGE, which is a software-defined sensor network for AI at the edge. Scott went into already quite a bit of detail about this, but basically what we're trying to do is develop an infrastructure for deploying AI problems at the edge. And this is going to be used for solving scientific issues such as understanding resilience, like why do ecosystems, cities, and neighborhoods respond differently to phenomena such as gradual changes in weather or catastrophic events, as well as solving particular other science problems at the edge using machine learning. And what this is going to do, the basic concept here is that we have these sensors available at any sort of site, whether you have LiDARs, radars, cameras, whatever sensor that you can use for your scientific problem. And they will be coupled with edge computing devices at the edge that will go in and solve these machine learning problems at the edge. Now what that'll do is it will compress the data and then send it to an HPC platform, which will then do some of the harder number grinding here, and then you can send it back to that edge compute device, and then that edge compute device will be able to communicate with the sensors at the edge for guiding how these sensors should detect and sample the data at the edge. So particularly arming the edge is going to focus on how this infrastructure works for the Doppler LiDAR system. So we're going to deploy wild SAGE nodes, and we've already deployed a SAGE blade at the SGP site, and we are going to couple these architectures together to determine how to best determine the sampling coming from the Doppler LiDAR. Now, in particular, I will show why here we're going to be focusing on the Doppler LiDAR. So at the SGP site, we have years of data from this Doppler LiDAR, and what we need to get from it are key components of these. What we need to get from this is the properties of the clouds and rainfall that need to be from represented processes at the scale of cloud drops and drizzle and climate models. Now, what the LiDAR here is recording, it's recording a rain backscatter signature and a cloud backscatter signature. So you're going to get signatures from multiple sizes of drops. Now, in our current processing for the Doppler LiDAR, as you get this signal, most of this raw data is too large to be transmitted, in particular through the network bandwidth. So what we have to do is compress this raw signal into quantities that are understandable for atmospheric scientists. So first we want to do at the edge is process the raw, what we call IQ data, and I developed a package called HiIQ to process some of this raw data into what we call Doppler spectra. Now what the Doppler spectra show is what we see here on the right is the distribution of velocities of the scatterers relative to the LiDAR beam. And in many cases at SGP, we get multiple peaks corresponding to different populations of particles. For example, we have raindrops that have higher fall speeds relative to cloud droplets, which would expect to have lower fall speeds in the air. And what we want to get from these are what called Doppler moments. And common moments are signal to noise ratio, Doppler velocity, spectral width. But these moments are also expensive to calculate and consume, and you can consume much bandwidth over the network if you keep the whole Doppler spectra there. So what we want to answer is, when do we need to calculate and transfer these detailed cloud information for cloud process studies? right now we don't transfer nearly all this information over to the ARM user. We merely transfer SNRs as well as velocities, assuming the highest peak here in this Doppler spectra. Now, if you were to say, if you just did the Doppler spectra from the highest peak, you're going to be removing a lot of information about the rainfall that is present. So you're going to, in particular, you're going to in particular be losing a lot of vital information about the microphysics of the clouds that we are sampling. So first, applying this high IQ data to some example Doppler LiDAR data on August 2017, we can see at the top that is the default processing and made in the from the stock hardware on the top from the Doppler velocity. And as you can see, there are many discontinuities present in the stock processing that is simply due to the fact that the one peak becomes more dominant than the other. So sometimes it'll be recording the rain peak for fall speed, or it'll be recording the cloud peak. But if we use our GPU-based processing, you get a much more realistic picture of this rainfall coming from the Doppler LiDAR, as you can see below. And we're able to do this processing of the edge for about a minute for a whole day of data. So this can be done very quickly and on demand. After doing this, we'll want to apply machine learning to these different images, so we can get an idea of when do we need to actually do this data transfer, so that we can save room and save bandwidth, so we don't overload the ARM infrastructure with all this massive amount of data. So I've tested out two different machine learning models. First was called gradient boosting machines, and particularly I'm using the XGBoost implementation of the GBM. But what we do here is that we will train the model based off of decision trees, and we keep adding on decision trees as we go until we are able to further refine, until we are able to minimize the amount of error between the classification and the real labels in the data set. So what I did is that I took 3 months of ARM Doppler LiDAR data, and I manually labeled it clear, cloudy, and rainy according to what the conditions that were going on at the time, looking at different NextRad data and satellite data, and also looking at observations in Oklahoma to determine whether at the S2P site in particular, to determine whether we were clouds, rain, or clear. Now, so if you're just alone, it's difficult to perform machine learning without some sort of reduction, whether it's a convolution or whether you want to actually take the image and perform a statistical coverage product. So my first approach here, I actually take the 5-minute images of signal to noise ratio, and at 200-meter height intervals, get the percent of height interval with signal noise ratio greater than a certain threshold dB. Now, what thresholds do we use? How many boosting rounds do we need? These are all the various hyperparameters that I looked at and try to be able to optimize as we go through. And I use early stopping and 5-fold cross-validation to determine that the most optimal option was around 1,300 boosting rounds with using the statistical coverage thresholds for 3 and 10 dB. And that gave me the best training and testing accuracy for determining whether we're clear, cloud, and rainy. Now, what I'm looking at here next, I am defining a positive here as a time when we're cloudy and rainy, and a negative is clear. So for the terms of specificity and sensitivity, we can distinguish between these time periods. They're well over 99%. So it's working very well there. And if we get to the actual accuracy to prediction, we can get up to about 94% accuracy to distinguish between the clear, cloudy, and rainy conditions. So this is not bad, considering this fairly simplistic implementation of the machine learning model. So this one thing that does give me some confidence, is that given the speed of XGBoost, it's very fast. This is something, in particular, you can do this classification in a split second. Gives me something that I can very confidently put on an edge computing device to be able to classify some of these time periods. Now, the other question I have is, how much would we be saving here? Well, if we look at the data set, this 2.5-month data set here, about 80% of the time periods are clear. So we only really need to do this processing about 20% of the time. So having this sort of advantage here, when applying this algorithm to the edge, would definitely save us a lot of bandwidth for when we don't need the extra cloud microphysical quantities. But at the same time, we can refine our data processing to the most interesting time periods we need while cutting out 80% of the data. And that's going to save us a great amount of space and bandwidth as we go along. Now, the one limitation there is here is that sometimes you get into rainy conditions and it has some trouble distinguishing from clear, because you can see in the confusion matrix here on the right, you have about a little under half of the clear, the rainy conditions identified as clear. So it's having some trouble there. It has its limitations, and it also something now look at why this is the case, and in particular, see if I can make improvements on that. I'm also testing out a neural network approach, which I think most of the room here is familiar with, at least how neural network works. You have layers of nodes, and you have data that you train the weights of these nodes with according to the data that you input in the nodes to put in an output layer. But I'm also trying a neural network approach where I'm just taking in a 5-minute image of SNR through a 3-layer convolutional neural network, flattening it, and then putting it through a dense ReLU layer, and then a softmax layer to classify it into 3 classes. And this so far is not giving me as much, this confusion matrix here, is not giving me nearly the amount of skill that I am going through the XGBoost model. While I'm still investigating more different configurations for this, currently the XGBoost model is providing more promise for being able to do this classification. But I also want to test out different CNNs, and this is a current work in progress for me. So in conclusion, the current R facility infrastructure doesn't permit transfer of the detailed amount of microphysical data from the Doppler LiDAR due to bandwidth constraints. So I need to get much more information. A lot of information about the cloud and drizzle properties is lost in the simple transfer. I developed some software for GPU edge computing processing of the microphysical properties using the SAGE architecture, and the gradient boosted machines applied at the simplest moments can be used to guide when more detailed processing is needed. And one of my next steps too is also test out this GBM algorithm on the virtual Waggle nodes and on the SAGE blade that is deployed at SGP. So if you have any questions, I'd be welcome to take them now.
Sure, so go ahead and post your questions in the chat or the Q&A. While we're waiting for those to come in, first of all, it's good to see people doing GPU-based computing for some of the INQ processing. Maybe I just missed it. What were you using for your ground truth for your data set? And then also, what was your validation split?
Okay, so the ground truth is manual classification of data for the 3-month period using satellite and radar observations. And the training test split is 80-20, is 80% training, 20% testing.
What about a validation split for the hyperparameter tuning you're doing?
Oh, that's a 5-fold cross-validation.
Okay. Yeah, you mentioned that. Thanks.